Hello everyone, welcome to COMP359, Design and Analysis of Algorithms. In this video, we are going to start our discussion about divide and conquer. I will first talk about merge sort, and mainly the focus of this video is to see how we can analyze the time complexity of problems that we solve them using recursive algorithms. Merge sort, I'm sure that you are already familiar with merge sort in COMP359 and maybe other actually courses. Merge sort will be solved using the idea of divide and conquer. So the whole approach of divide and conquer is to try to, break the problem to a smaller sub-problems, solve them. So the conquer part is just conquering the smaller sub-problems, and then using the solution for the smaller sub-problems, you solve the original problem. So merge sort, the problem is sorting. We have a list of items, we wanted to sort them. The idea of the merge sort is to divide our list of items into two parts, two halves, and sort each of these halves, right? So this is going to be that conquering step. And then after you have two sorted sub-arrays, combine them to get the list of full items, original list, in the sorted format. So that last part is going to be actually the actually combining the solutions or the merging. So let's just get back to the idea of the merge sort. Dividing the problem to sub-problems is easy, right? Solving the sub-problems is going to be that recursive part of the solution. So each of these sub-problems are going to be solved using the merge sort. So the only part that remains that we need to actually solve is this combining part, merging part. How can we merge two sub-arrays which are sorted and get a full list of items which are the final solution should be sorted? Is it simpler than the original problem, which was sorting? We already know that, yes, we can actually combine two sorted sub-arrays using an algorithm which works in linear time. What was the algorithm? Assume that I have two sub-arrays, right? Both of them are sorted. I would create a new array which the size of it is going to be the summation of all the items, the summation of the size of this list and this list. So among all of the items that we have, we are looking for the smallest one to put in this actually index. Where is the smallest one? The smallest one is going to be either the smallest in this list or the smallest in this list. So you can see that I have created two pointers, each one, let me choose a different color, each one on one of these sub-arrays, and one pointer that is starting on the beginning of the the new array that we are going to fill. So you compare the smallest item from this list, the smallest item from this list. The smaller one is going to be the smallest among all the items, which is going to be 5 here, and it will be copied here. Then what is going to be the next smallest item? It is going to be either this one or this one. You compare them, get the smaller one, and copy it here, which this time is going to be 12. And you just continue just comparing the two items from the two sub-arrays, and each time copy one of them to the new array, and you continue until one of these pointers reaches to the end, right? And in that case, the rest of the items from the other sub-arrays will be immediately copied. So what's going to be the time complexity of such algorithm? I think it's clear that the time complexity here is going to be O of n, where n is going to be the total number of items that you are actually sorting, or you are merging here, right? Whatever is the number of items here, this is going to, the total time complexity is going to be O of n, because for each of these items you did just one comparison and just some assignment and copying and incrementing the pointers. So a fixed amount of work for each of the items. How many items you have? N number of items. So it's just like you have C multiplied by N as the cost, as the time function for this algorithm. And so this is going to be the total time complexity of merging is going to be theta of N, or we can write it as O of N. Actually, usually both of them are going to be the same. Even if you are not convinced with that intuition, you can write down the full algorithm for merging and just analyze the time complexity, find the time function for the merge. Here is a simple algorithm for merging two sub-arrays, and you can actually just verify that the time complexity is going to be a linear O of n. You have this loop which actually is doing the main work, comparing two items from two sub-arrays and each time copying the smaller one to the new array. And these two actually small loops that you see is just for copying. Whenever actually the one of the pointers reaches to the end, the rest of the other array needs to be copied, right? So either this loop will be executed or this one. Anyway, at the end, when you analyze this algorithm, this pseudocode here, you can actually see that yes, the time complexity of merge is going to be linear. So now that we are done with finding a merging algorithm, we need to actually get back to the original problem of a merge sort. So the original problem was to divide the problem to the original algorithm was to divide the problem to smaller subproblems, solve them, and then actually combine them to get the full solution. So for that part of solving the smaller subproblems, we need to recursively call the merge sort. So the full pseudocode for merge sort is going to be something like this. This is a recursive algorithm, so of course you need to have a base case for your recursion. Here you can see the base case that is talking about the case that if the size of the array is equal to 1 or 0, so it's just like you have no item or you have just one item in your array. So in that case there is no sorting, right? An array of size 1 or 0 is already sorted. So you just return the array. Otherwise, you will actually call the sorting over the first half, call the sorting over the second half. So you can see that this is a recursion call. This is a recursive call, right? And then you merge these two parts, okay, and then return the sorted array. This is just a pseudocode, of course. You know that I'm not talking about the details of the implementation. So now what we are interested for the rest of the video is to see how we can analyze the time complexity of algorithms like merge sort, algorithms that works based on recursive idea. You can see that in this algorithm, it's not that easy like, for example, the merge function. In this merge function, you can see that every computation is clear. I can simply find the time function and then analyze that time function saying that, okay, this is going to be theta of n, for example. But in this pseudocode, I have two recursive calls. So how can I find the time function for this problem, for this algorithm? We have actually briefly talked about finding the time function for recursive algorithms in COMP359, but in this course, I will go in more depth and we will see a lot of examples. In fact, many of the algorithms that we will see during the course will be recursive algorithms, and that's why I'm actually spending this week focusing on analyzing the time complexity of recursive algorithms and in fact learning how we can solve the reoccurrence relations. So let's just look at the merge sort and see that how we can find the time function for merge sort. Let me actually just clean up here a little bit. So what we are interested here is to find the time function, which is going to be called, we are going to call it T of n. This is going to be how much time we would need to solve, to actually run merge sort over an array of size n. Again, here you can see that this n is going to be the variable that determines the size of our problem. The size of our problem here is the size of the array. So we wanted to know what is going to be, how much time based on n we would need to solve, to run merge sort over an array of size n. So if you look at the full algorithm of merge sort, I have some comparison and some actually returning. So the total cost of this part is going to be a constant amount of work, right? I can write it as O of 1, for example, or you can write it as C to show that this is going to be some constant amount of work. Then I have a recursive call. I don't know how much time here it is going to take. But what I know that this is going to be the same function as the main merge sort, right? So if the merge sort over an array of size n is going to take T of n much time, so how much time it would take to actually call the same algorithm over an array of size half? This is going to be, I don't know how much exactly, but I can say that this is going to be T of n divided by 2. You can see that I just divided that argument. On this line, I have again another call of the merge sort. And again, the size, although this is going to be the second half, but I just care about the size. It is going to be half of the array. So the cost for this term is going to be T of n divided by 2 again. So this term and this term are both the same. And at the end, I am going to have a merge function. What was the cost of this? We already actually discussed that. That was going to be theta of n, or you can write it as O of n as well. So now I'm going to actually get back to here, say that what is going to be the full T of n? That is going to be the summation of all these terms that I found here. So at the end, what I'm going to have is going to be 2T of n divided by 2, right, for this term and this term. Plus, I can just write it as theta of n, because this C, actually constant amount of work, can be simply just ignored. So, or you can actually just write it instead of theta, you can actually write it in this way as well. 2T of n divided by 2 plus, for example, Cn. If you are going to be very precise, you can even actually just add another constant as a fixed constant as well, but I don't really actually mind if you just leave that one out. So the full actually time function that you have is going to be a relation like this. And this relation is going to be a recursive relation or reoccurrence relation. Why? Because of this term, right? This is exactly the same term as the t of n, the same function, but just with n divided by 2. So the rest of the video is to actually discuss how we can solve reoccurrence relations like this. And at the end, figure out that what is going to be t of n. It is going to be, for example, theta of n, it's going to be theta of n power 2, theta of n log n. What is going to be t of n? So, okay, we are here having finding our reoccurrence relation. Now we need to actually solve this recurrence relation. So for the simplicity, what I'm going to actually do here when solving this reoccurrence relation is that I'm going to assume n is some power of 2. Let's just actually say that, call it 2 power k. This simplicity is not going to, in fact, lose the generality of the problem. You can actually read more about the details of it in your textbook, but the fact is we can prove that for any value of, and it doesn't really matter that if you consider it as some power of 2, later on we can actually say that for any value of n, the discussion here is going to be valid. But here, just for simplicity of this, solving this, I'm going to assume that this is going to be, n is going to be some power of 2. And the reason for actually considering that is because here I'm actually dividing n by 2, and that's why I'm doing this assumption. So how I'm going to actually solve this reoccurrence relation? In your textbook, a couple of different solutions has been discussed. I am going to focus on 2 of them, using a reoccurrence tree and the other one using the substitution method. So let me actually, before going to the next slide and showing you that, let me actually show you that how we can create the reoccurrence. Let me create a new slide. I wanted to see that. How can I? Okay, let's just add an empty slide here. Okay, so the recursive relation that we had was t of n is equal to 2 t of n divided by 2 plus cn. I'm saying if you wanted to be very precise, you can actually add another term as c prime as well. Okay, so what is the idea of reoccurrence? What is the idea of that recursive tree or reoccurrence tree? In fact, when you actually think of t of n, okay, just think about this. T of n is a problem, right? You are solving it. It's just like here, t of n for us is going to be that merge sort, calling the merge sort. You can just think about each of this as a function call, right? If you go back to your original actually algorithm, you can just think of t of n as original function call for sorting an array. So I have a box that shows that what is the cost of the first recursive call of the merge sort. What is the cost of that? You can see that I have 2 terms of t of n divided by 2 because I don't know what are the cost of each of those, I can write them as actually two boxes like this. T of n divided by 2 and another T of n divided by 2. It's just like when you are in this function call, you are calling another merge sort of half size, one merge sort of another half size, right? And in addition to these two costs, you also have, in fact, this cost, right? Which is going to be the cost of your merge. Okay, so I'm going to write down those costs which I'm sure about them here. So Cn plus C prime. So what is going to be the cost of T of n? The cost of T of n is going to be, the cost of T of n is going to be this cost plus whatever is going to be the cost of this box plus whatever is going to be the cost of this box. Okay, so what I'm going to do is just doing the same analysis for each of these T of n divided by 2. So it's just like recursively I am applying the same. I'm saying that what is the T of n divided by 2? T of n divided by 2, I don't know anything about it except that this is going to be the same formula, recursive formula as T of n. So I can say that T of n divided by 2 will be 2 T of n divided by 4. Why? Because you can see that I already have n divided by 2 here. I would divide it by 2 again, so it's going to be n divided by 2 by divided by 2, so it's going to be n divided by 4. Plus C n divided by 2 plus C prime. Right? So it's just like I just replicate the same formula for n divided by 2. So I am going to have two boxes of n divided by 4, another box of T of n divided by 4. And for each of these, there is going, and for this box, there is going to be another term of this cost, right? C of n divided by 2 plus C prime, right? And all of this discussion is going to be applied to this box as well. T of n divided by 4, T of n divided by 4, and there is going to be an additional cost of C of n divided by 2 plus C prime. Okay, so I can do the same discussion for all of these actually boxes. And you can see that by doing all of these discussions, level by level, actually applying the same recursive relation for all of this and growing it, what you are going to have is, in fact, a tree, right? You can just think of it as this is going to be the root of the tree, and it is growing. It's going to be just like a binary tree, because each time, each of these boxes will go to two other boxes. So the whole shape is going to be like a tree. And what are going to be the leaves when we are going to actually stop? We are going to stop when we reach to T of 1, right? It is in fact actually just telling you that whatever is going to be in the argument of T is going to reach to 1. This is exactly the, all of these boxes that we have here in this actually tree shape are going to be the function calls if you write merge sort, if you actually write merge sort in Java, Python, whatever programming languages, and you execute it on the computer, each of these boxes is just like, a function call that would be executed, would be called on the computer. And this is exactly what we need. So at the end, it's just like you are going to calculate how many number of these boxes, which are going to be the time functions, the function calls, are going to be executed, and for each one, how much time has been spent. So at the end, what is going to be, the summation of all the costs for each of these boxes, for whatever is going to be all of each of these boxes, all the costs that you have associated to each of these boxes are going to be the time that will be spent on the computer to execute the full merge sort, which is going to be this function call. This is the original function call, and you need to get the summation of all of these costs to find the full amount of time that is required, that will be spent to execute the merge sort on the computer. So now let's just, this is the idea behind this reoccurrence tree. So let me actually now show you a more clean actually picture here. This is showing you the full, that binary tree, the tree of all those function calls. Let's just call it just a reoccurrence tree, as your textbook call it. And don't forget, each of these boxes are in fact just representing a function call, t of something. And we need to find the cost for each of these boxes, get the summation over all of that to figure out what is going to be the cost. So what is going to be the cost of each of these boxes? The cost of each of these boxes, you see the sizes, almost actually I showed those costs using these little green boxes that I put over this. But to be more, in fact, again, accurate, that costs that we are working over it can be represented as a polynomial term like Cn plus C prime. But even if you just write it as n, that is going to be enough for me. I wrote the full, formulas just for this example to just make you sure that we are not really by leaving out some of the details, like by leaving out these costs at the end, there is no difference. Even if I just write it as n or Cn plus C prime, the result is going to be the same. But for now, let's just actually stick to the plan and stick to the full formula that we have here. So for the first level, for this, you can, I'm going to actually get the summation of the cost of over all of these boxes, right? But I'm going to do it level by level. So for example, at this level of the tree, how much cost I have, at this level of the tree, how much cost I have, and then I will get the summation over all of them. So the cost of this level, I just have one node in the tree, and the cost of that's going to be Cn plus C prime. The cost in this level, it's going to be the cost of this box and the cost of this box. So if you get the summation, this is going to be the cost of each of those boxes, and I have two identical boxes in that level, right? So that's why I'm multiplying it by 2. In the second level, I have 4 boxes, each one the cost of it is going to be Cn divided by 4 plus C prime. And you can see that I just wrote n divided by 4 as 2 power 2. So it's just like you can see that each time I am adding 1 power of 2 in these levels, dividing it by 2, dividing it by 4, in the next level dividing it by 8, and so on. Until I will reach to t of 1. So now the question is, how many levels this tree is going to have? One interesting thing about the costs of each level that I can actually see here is that I can simplify the cost of each of these levels and see that, okay, these 2 that you are multiplying, and then it will be 2 power 2. These are going to be, if you multiply it inside the parentheses, this term is going to actually remove this term, right? And at the end, what I am going to actually have can be simplified as a summation like this. Okay, where this part is showing the summation of all these terms. I have added up all of these terms, and you can see that I can simplify it in this form. We can definitely actually see the okay, not just this term, but the whole actually term here. This Cn multiplied by k is going to be this part of it, and then when you multiply that one into C prime, you are going to actually get the this sigma part. Okay, let me actually do a little bit clean up here. You can, in fact, just pause the video here and play with this formula. Try to, adds up all of these terms that we have here and see that this is going to be exactly this summation. This part of this sigma part is going to be when you are multiplying this term into C prime, and this part of it is going to be actually the summation of all of these terms. The fact is, this term in all of the cases here is going to be Cn. Here it's going to be Cn. Here it's going to be Cn. But this term is going to be actually varies. C prime. That is going to be actually all the powers of 2 to the power of I. So what is k? Again, let's just actually get back to that. What is k? K is going to be the number of levels in this recurrence tree that I have created. So how many levels this tree is going to have? You started from n. Each time you are dividing n by 2, and you stop when n, in fact the number in the argument of t reaches to 1. So you keep dividing n by 2, and the total number of times that you are dividing n by 2 until you reach to 1, so it's just like n divided by 2 power k reaches to 1. So this is going to be exactly this value, right? So you will stop when n divided by 2 power k is equal to 1. I can simplify this and say that n is equal to 2 to the power of k. Remember, we actually simplified and assumed that at the beginning, we assumed that n is going to be some powers of 2, right? 2 to the actual power k. So I can say that k will be the log of n in base 2. Okay, so now let's just use this number to simplify this formula. Okay, here we have this term, and I have actually simplified this summation using this formula from the discrete math. If you don't remember it, I would recommend you to just review discrete math. So we know that the summation of all powers of 2 from 0 to k minus 1 is going to be equal to 2 to the power of k. If the upper bound of this summation is k minus 1, the final the summation of all the powers is going to be equal to 2 to the power of k. What is 2 to the power of k? It's going to be equal to n. So it's just like this term will be equal to c prime n. What is going to be this term? This term is going to be cn plus log n. K is equal to log of n, right? So I'm going to have cn plus log n, and the other term is c prime n. The total actually time complexity in terms of the lambda notation, I can write it as big O of n log n, or I can write it as theta of n log n. There's in fact no difference in that. Both of them are correct, but maybe to be more accurate, you should write it as theta. I mean, more precise. Okay, this approach was called reoccurrence tree. I think this is going to be section 4.3 or 4.4. I don't exactly remember in your textbook. But this is reoccurrence tree, and the whole idea is that you would create a tree like this and calculate the time, how much time you would need for all of these actually nodes in the tree, get the summation over all of it, and so at the end you can actually just find out, you get a formula, a simple formula like this. Another approach to solve the reoccurrence trees is to use the substitution method. Some of the reoccurrence relations are, it just depends that what problem you are solving. Sometimes you can simply just use the substitution approach. Sometimes it is much easier if you actually use the tree. I personally always prefer to use the tree, especially if I have, something like this in your formula. You have some multiplication, it's just like in your algorithm, you have more than one sub problem. So in that case, the tree is going to be much easier to use. But I'm going to solve the same reoccurrence relation using the substitution method here and show you that both of them are going to give you the same result. So here again, this problem that I have, the original reoccurrence relation that I have is this one. T of n is equal to 2t of n divided by 2 plus cn. And I know that when n reaches to 1, the cost is going to be constant. Okay, so t of n is equal to 2t of n divided by 2. The substitution method is just telling you that, okay, get this term and replace it by the same recursive relation. So again, we know that t of n divided by 2. What is going to be the relation for this? It is going to apply the same relation as t of n. So that's going to be 2t of n divided by 2 divided by 2, right? Plus c, what is that n? This is going to be n divided by 2, right? C n divided by 2. Let me just... Okay, if I wanted to simplify this formula, I'm going to actually reach to 2 t of n divided by 2 to the power of 2 plus cn divided by 2. This is going to be equal to t of n divided by 2. I'm going to get the same, this actually term, and replace it here. So the result here is going to be 2t of n. Let me actually, I forgot something. 2 multiplied by 2 t of n divided by 2 to the power of 2 plus c n divided by 2. So now if I multiply this term 2 inside the whole bracket, I will reach to this relation, 2 to the power of 2 t of n divided by 2 to the power of 2 plus cn, right? Okay, I then will apply the same formula over this term. So that's why we call it actually substitution. We just keep substituting these recursive calls with the actually the same relation again and again. What is going to be t of n divided by? This is going to be 2 t of n divided by 2 to the power of 3 plus c of n divided by 2 to the power of 2. I will get this and put it inside instead of actually this one. And I'm going to actually just, let's just do that. 2t of n divided by 2 to the power of 2 plus some cn divided by 2 to the power of 2. If you multiply this term inside the bracket, you will get I missed this one. Okay, you would get 2 to the power of 3 t of n divided by 2 to the power of 3 plus cn. Again, you can see that actually this term is going to be fixed. Plus that cn. Plus cn. So it's just like, you know, that if you need to add up those terms of cn that I forgot to add previously, but now you can actually see that I am going to have 3 terms of cn. So this is going to be t of n after 3 steps of substituting the recursive relation. If you look at the formula, you can see a very nice pattern. After 3 steps, I am having a term here, the same and the same. So how many steps I will go down and replace this t of something function in this? How many steps until you will reach to actually term equal to 1. So you will continue this substitution until n divided by 2 to the power of k is equal to 1. So you will actually continue until k steps, which k is going to be log of n. And in that steps, it's just like what you are going to have is 2 to the power of k, t of n divided by 2 to the power of k, plus k c n. Okay, you will actually go until you reach to this, where k is equal to log of n. And this part is going to be equal to 1, so this term can be replaced with some constant, or you can replace it by 1. Okay, so it's just like I can simplify it as 2 to the power of k multiplied by some c prime plus k c n. 2 to the power of k is going to be equal to n, right? So this part is going to be c prime n, and this part is going to be c n log n, where log n is equal to k. So what is going to be the final result of this reoccurrence? This is a leading term, so the total time complexity is going to be theta of n log n. I have written the full that substitution in a cleaner way here for you. You can just follow it on these slides if you like. So these two different approaches, substitution method or reoccurrence tree, both of them can help you to solve many reoccurrence relations like the examples here. Okay, you can try to actually solve the exercises, these exercises at home. I have actually solved one of them here. If you had more questions, we can solve a couple of them in class or during the office hours. So let me actually just discuss about, for example, this reoccurrence relation. T of n is equal to 2t of n divided by 2 plus 1. Here again, because of this actually n dividing by 2, I can assume that n is going to be some powers of 2. Okay, so this is just an assumption that's not going to lose the generality of the problem for us. So using the reoccurrence tree, because of actually having this two term, you can either use the substitution approach. I mean, both of them should give you the same result, the same solution. If you got two different actual solutions using the substitution or reoccurrence tree, definitely one of them is going to be wrong. Usually, I prefer the reoccurrence tree because it's more visual and gives you, a better idea and less likely to miss anything. So the reoccurrence tree here, because you have two terms of tn plus 2, is going to be very similar to what we discussed for the merge sort. That relation was 2t of n divided by 2 plus n, and here you have actually 1 as an additional cost. So it makes it completely different, although they look the same. So although the reoccurrence tree is going to be similar because of the term 2 and the fact that each time you are dividing n by 2, right? So from t of n, you are going to have two actually other boxes of both of them of t of n divided by 2, and then for each of them you are going to have two boxes of t of n divided by 4, and you continue until you reach to the t of 1. But for each of these boxes you are going to add some cost. That cost here is going to be 1 or any fixed amount of cost. Okay, so it's just like you are going to add an additional cost of 1 to all of these boxes. So now you might actually just feel a little bit confused. In the previous actually reoccurrence tree, we had some costs which are actually n, and this is n because the reoccurrence relation was t of n divided t of n is 2t of n divided by 2 plus n. Okay, so this n is in fact coming from this cost. Here in this relation, I have it as 1. But the rest of the approach is going to be the same. You just need to add all of these costs, all of these ones, over all of these boxes. Okay? So to make it simpler for you, you can actually just think of it as, okay, how many boxes, it's just like how many nodes in this binary tree you are going to have. It's going to depend on the, in fact, again, depend on the depth of the tree or how many levels you are going to have. So at the first level, the total amount of cost is going to be 1. At the second level, the total amount of cost is going to be 1 plus 1 because you have 2 boxes, right? So it's going to be 2. At the third level, it's going to be how many boxes you have. You are going to have 4, so 2 to the power of 4, until the last level, which is going to be how many boxes you are going to have. This is going to be the number of leaves. This is going to be 2 to the power of k, whatever is going to be the number or the depths of this tree, which the depth of the tree is going to be, in fact, that when n divided by 2 to the power of k reaches to 1, so where k is going to be log of n. Okay, so I need to get the summation of all of this cost. So again, this is going to be that popular summation of I equal to 0 to the power of k 2 to the power of I. So, and this is going to be 2 to the power of k plus 1, which is going to be equal to 2n. So t of n is equal to 2n, which means that, 2n, which means that t of n is in fact theta of n. Okay, so the final solution for t of n is going to be, the final result for t of n is going to be theta of n, and we just prove it using the reoccurrence tree. This is going to be the final result. I have actually a couple of additional slides here that is talking about using induction. I haven't actually seen it in your textbook, but I found this approach was also very interesting. Just reads it as additional discussion, which in fact actually discussed that how we can use induction to prove the that, for example, some guesses that we have for reoccurrence relations is going to be correct. I'm going to actually skip it for the video, but you can find the full description here in the slides, and an interesting question at the end with its in fact solution. So if you had any question, we can discuss it in class or during the office hours. So I'm going to finish this video. This is going to be covering chapter 4, sections 4.1 to 4.4. That's mainly discussing how we can solve the reoccurrence relations, either using the reoccurrence tree or using the substitution method. In the next video, we will talk about a very more general approach that helps you to solve the reoccurrence relations called master theorem.